Hi, everyone, and welcome to our webinar on new tips and tricks that every ClickHouse developer should know. My name is Robert Hodges. I work for Altinity, and I'll be your presenter today. I'm backed up by the Altinity team. We'll introduce them shortly. Before we go too far into this, I'd like to just talk about a few things that will help you enjoy this webinar more. First of all, it is being recorded, and we will send a link to the recording as well as to the slides to everyone who has signed up after the webinar is over. You'll probably get them within about 24 hours. Second thing, we have time for questions, and you can either enter them in the Q&A box or you can put them in chat. It doesn't really matter which you do. My colleague Chiara Toselli is watching the chat and the questions, and will highlight them as they come up. If they're relevant to what I'm talking about, I'll just answer them right then and there. Otherwise, we can defer them to the end. I think those are the main things to enjoy this. So let's dive into the content. So what I'd like to do first is just do some quick introductions. Oh, by the way, let me do one quick thing. Chiara, is sound good?
Sound is good, yes.
Okay, great. Thank you. Just want to make sure that we've got good sound coming out to everybody who's attending. Introductions. So my name is Robert Hodges. As I said, I'm a database geek. I've been working on databases for 40 years. Over 30, of course, is also correct, but it sounds less old. I started with pre-relational systems, worked at places like Sybase, worked on MySQL for many years, and now I'm working on ClickHouse, which is those three databases I named are my favorite databases of all time, and ClickHouse is the current one. My day job is I'm Altinity CEO, so I'm responsible for running the business, but I really like database technology, and I do a lot of these presentations, so I hope you'll enjoy this one. The only way I can do this is that I'm backed up by the Altinity engineering team, and this is a great team of engineers, enormous amount of database experience. Cumulatively, we have many centuries of experience in running database systems, and particularly analytic systems, which are the focus, of course, of today's talk. And then a little bit about Altinity. We are an enterprise provider for ClickHouse. Enterprise support. We also have a cloud platform, Altinity.cloud. It was the first cloud for ClickHouse that was introduced in Amazon and also GCP. It's grown very rapidly over the last 2.5 years, and is a great place if you'd like to have managed ClickHouse. We're also major contributors to open source. Of course, we contribute to ClickHouse itself. We're authors of the Kubernetes operator for ClickHouse, which some of the people on this call almost certainly use, and many other open source projects, but we're very, very big on Kubernetes. And in fact, all of our cloud technology is based on that. So that's a little bit about us. Let's introduce ClickHouse. So for the few people on this call who've never heard of it, it's a real-time database. Our analytic database, I should say. It understands SQL. So in that sense, it's a bit like MySQL or Postgres or other databases you're familiar with. It runs everywhere. So bare metal to cloud. That's true of both Postgres and MySQL. It's also open source. It has an Apache 2.0 license, very favorable license, particularly if you sort of well understood by companies, and you can use that to sort of distribute it in any way you want. There are very few limitations on what you can do with it. On the analytics side, it has what's called a shared nothing architecture, which is where you have compute nodes connected by a network, and each owning patches of storage that they manage and run query on. Over time, ClickHouse is iteratively moving toward a separated compute and storage model, but this is something that's still a work in progress. Parts of it work well, parts of it are yet to come. Like most analytic databases, it stores databases in columns, highly compressed columns. We'll talk a little bit about that in one of the tricks. And it's extremely good at executing things in parallel. This is another thing we will talk about, using both vectorized execution, which is where we break up the data, this column of data, break it up into arrays, push it onto the CPU, take advantage of things like single instruction, multiple data instruction to do things like sums and other mathematical operations quickly. It can also spread queries across many nodes so that you get the power of both the I/O capacity as well as the compute capacity of multiple machines working together to answer a query quickly. And it's incredibly scalable. So there are companies like Cloudflare, for example, that have tens of petabytes. They're very well known. We have customers that run ClickHouse clusters with hundreds of nodes. Uh, it underlies things like analytics at Microsoft for Bing. If you've ever used Microsoft Clarity, that's also driven by ClickHouse. It's a very, very powerful and widely used analytic database. And in fact, it's become a core engine across a wide range of industries as the driver for low latency analytics. Basically anywhere that you have a lot of data and you need to give answers on it quickly. So that's ClickHouse. Let's get in and show some tricks. Before I do that though, I'd like to just talk about the original tips and tricks talk. I did this about 4 years, well, 3.5 years ago. And it was a very popular talk. We have it up on, it was originally a meetup talk, and it is, then we put it on YouTube. It's had thousands of views, but it suggested a bunch of basic things that you could do to just make ClickHouse work better, faster, more cost efficiently. And here's the list. I won't bore you with them. You can in fact just look up that, if you Google that link, tips and tricks every ClickHouse user should know, you should come up with a YouTube video that's on our channel, and it will talk about all of these things. And if you go look at that, most of them are still good today. There's only really one that I would uh, uh, sort of qualify a bit, which is use replication instead of backups. That's actually something that has changed quite a bit in ClickHouse. There are better backup mechanisms, and we do recommend using them. All of the clouds that support ClickHouse have good backup now. So, but this is a great place to start. And what I'm going to do in this new talk is basically talk about some new tips and tricks. I've got 7 of them. I am going to repeat a little bit of one, which is to talk about encodings, because they're so critical to managing the data and making and arranging it efficiently. So we're going to repeat that a little bit, but all the other stuff is new. And as we go into the tips and tricks, I'm also going to try and talk a little bit about what's going on behind the scenes, because the thing about these tips is if you understand the tip and you understand how it works, you in fact understand how to do other tricks with ClickHouse because you know what's going on in the plumbing underneath. So let's dive in. First one, this is something that is a big change over the last few years, and that's the ability for ClickHouse to read S3 data. ClickHouse has added this. I think S3 has been around in some form or another for about 3 years, but it wasn't very good at the beginning. It has gotten way better. So let's dive in and show how to do it. So a typical way that you would read S3 data, and you could do this just because you're querying, just doing a direct query, or you're actually trying to read data lake information and put it into a table. And what you're typically going to do is use what's called an S3 table function. Table functions, if you're not familiar with them, they are functions that you can call in ClickHouse, and they return tabular results. So, and they can be used to wrap various types of things, everything from, these are also very similar to table engines. They can be used to wrap all kinds of objects and make them look like something that you can do a select on. So you'll set up the table engine, and you're going to have it pointing to, in this case, to S3. And in the examples I'm going to use, we're reading Parquet, but that's just one of many formats that ClickHouse can use. And you have a select, which is going to be select and some, some columns that you're going to be selecting. And then from S3, and then you'll be supplying some information to give ClickHouse a clue where you would like it to go look at this information. So here's how we do that. There's a new feature in ClickHouse that was introduced sometime back, probably a year and a half ago, something like that, called name collections. And these are super useful because it used to be in the S3 function and other table functions that you would actually have to supply a bunch of detailed information like URLs, credentials, all that stuff, which would go straight in the call. ClickHouse now has this feature called the name collection where you can basically supply the data and then it gets stored on the server. And in this particular case, we have information that tells us how to get to this. Where's the S3 bucket, credentials, the usual. This is Amazon, so the keys, and then what format it is. And this encapsulates the information about S3, and it allows us to read from it. One thing I'd like to highlight here is this use of wildcards. So you can see the bucket. There's the host, there's the bucket name, there's a so-called folder within it um, called orders, and then underneath that there are a bunch of tables which end with .parquet, and these are actually Parquet files which were generated in this particular example from Snowflake. So now we can go ahead and read from this, and this shows you here the form of the select. It's very simple because of this name collection. We have the data and we have everything encapsulated. So the S3 function invocation is very simple. Doesn't pollute your code, doesn't expose credentials, and then we can just do things like select aggregates off Parquet. And what this example here illustrates is now we can, because we're inside ClickHouse, we can now use the max threads setting, which allows us to control the number of vCPUs which are assigned or are going to be assigned to process the query. And so what I did was I just ran this query a bunch of times, and I set the basically doubled the setting on max threads each time from 2 up to 32, and you can see here that for the first 3 times, first 3 times I doubled it, it basically doubled my performance. And then by the time we get to 16, it tails off and it's just flat at 32. This is probably because of some sort of bandwidth restriction. This wasn't a particularly powerful host, but that's basically so you can see the parallelization effect. And what you can see is that by applying enough compute, we can get this to process in a pretty reasonable period of time. This was actually a query over 150 million lines inside Parquet. So a pretty good rate. And if you were loading data, if you're doing an insert, you in effect could actually do an insert of, since it's 150 lines, you can get it in 3 seconds. You can insert 50 million rows a second. That's not bad into a single host. So that gets us to a final part of this trick, which is to do parallel inserts. So on a single host, it's very simple. There's a couple of parameters that you want to set. Max threads, because it extends your covers your select. And then there's also a matching insert parameter called max insert threads. You can set that as well. And what it'll do is have parallel threads to do the insert. And then you can do a command like the following, where you just basically insert this data into orders by selecting straight from S3. This is a very, very fast way to read from a data lake into a single machine. What about if you have a cluster and with a bunch of shards? Well, it turns out there's a function called S3 cluster that you can use. It does not, to my knowledge, support named collections right now, so you have to set the arguments directly. But it can. What this will actually do is it will actually distribute the select as well as the insert across a bunch of machines in a ClickHouse cluster. So if you really want to get high speed, this is a way to load data very, very quickly from S3. So that's trick number 1. Here's a great question from Prashant. What's the max thread you can set? You can set it practically to any value. The question is, what will it help you? And the answer is by default, if you don't set it, max threads on ClickHouse will default to half of your vCPUs. In other words, because ClickHouse can see the Linux operating system, it says, hey, how many CPUs do I see? And or vCPUs as the case may be, and it'll give you half that number. You can generally set it up to the max. So like if you have 16 vCPUs on an Amazon or Google or Azure VM, you can use all 16. If you set it above that, it won't do you any good. And in fact, as we saw, you often see cases where it will flatten after a certain number of vCPUs. So uh, try it out and see how far it goes. Okay, great question. Let's go to tip number 2, and we'll start to pick up the pace here. Reducing storage size using codecs and compression. And as I said, this was something that was in the last talk, but it's such a great, it's such a great feature that it's something that everybody should be thinking about always whenever they're doing anything related to ClickHouse data. So let's start with a before picture. So this is a table that does sensor data readings. It's a bunch of test data. It has the example I'm going to be using has about 1 trillion rows in it, and you'll see uh, we'll talk about that in just a second. So here's the basic table, and what in this particular case, the table is not very optimized. There's a number of things that we can do to fix this, but for example, it doesn't pay particular attention to the data types. It doesn't care about partitioning or ordering. These are very important in MergeTree. We'll talk about more about those in a future tip. So this is going to be kind of slow. And in particular, it does nothing to transform the data so that it's stored most efficiently on disk. So let's talk about how we can do that. So when you're storing a column, the data in the column, you can think of it as a big array that's stored in a file, actually a couple files in most cases, and that file is going to be compressed. So the values in the column are going to be divided up into blocks. Each of those blocks is going to be compressed using something like by default LZ4, and or if you want it and specify it ZSTD1. What codecs do is they will actually take your input data and transform it before compression so that it becomes smaller. Low cardinality encoding, as it's called, is a form of codec. And basically what it does is if you have string values in your column, so for example, that's actually an airline tail number, uh, the so six letters. If you run it through low cardinality, it will actually turn it into what's called dictionary encoding. Instead of storing that string, we'll take all the strings that we have in the part and we'll make a dictionary where we just give them integer numbers. And so what that does is it takes this string, which is 6 bytes, reduces it to 2 bytes, and then it gets turned over to ZSTD. ZSTD compresses integer values very well, so we actually get something pretty small. So this can reduce the uh, uh, you know, uh, the amount of data that we're storing considerably. How do we actually apply that? Well, all you have to do is you modify your table definition using this codec uh, 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 keyword, which gives you the chance. And this shows examples of. We'll just take this first one. We're taking the integer value and we're applying what's called a double delta codec, and that stores not the value, the integer value that's in that column. It stores the change of the change or the slope of the slope. So imagine that you have a like a monotonically increasing integer, like say a monitoring data. It will basically store the uh, the slope of the slope. So how fast is it changing? And then how fast is that rate of change changing? This, a lot of words. This can result in for well-formed things like monitoring data that just keep increasing slowly. This can reduce your data enormously, like 99% or more. And then you turn the SAD remains over to ZSTD1, and you can get, in ideal cases, you can get compression rates of like 99.8%. It's ridiculously efficient. There's other types of codecs. Those are shown here. Low cardinality is used for strings. That's this dictionary encoding. It's typically used when you have 10,000 values or less. Unique values of the string within a part. It's quite effective. There's a couple of other little tricks here that I should mention. This alias is means that this is not a real column. It actually looks like a column and you can select off it, but it's really just a function call on another column. So a little bit more okay, sorry about had a temporary audio dropout. A little bit more expensive to run the alias, but this is a very cheap function, so it saves space and actually makes queries run faster. Some other things we've done in this table to optimize it is we've partitioned it by time, and we've also put an order by. When you think about reducing data size, the codecs are this and the compression are the single most important thing you can do. But the way that you order the data can also make compression work better by arranging values so that, for example, they are monotonically increasing. That just causes the codecs to work better. So you can also pay attention to that as well. The effect of all of these together can be really, really impressive. So this data set, as I say, runs to over 1 trillion rows. And here's an example. This is the number of bytes in the per row in the unoptimized table. You can already see it's pretty good. There's a lot of repetition in this data, so it was only 4.5 bytes per row for all that data. But as soon as we optimize the data types, put in the codecs, use LZ4 compression, which is not as efficient or not as doesn't compress as fully as ZSTD, we already got it down to 1.3 bytes per row. And if we use ZSTD, we can get it down to close to 1 byte per row. That means 1 trillion rows of data can be stored in a little over a terabyte. That's really great. And not only does that save you storage, which is of course important, but your queries run faster, often because they simply have to read less data, which is often one of the most expensive parts of the query. Just a quick up. We got a question coming up. I'll treat that in just a second. Quick comparison of codecs. These are the 6 that are currently supported. You can just read the table, but Delta, Double Delta, actually Double Delta and Gorilla are 2 we implemented at Altinity a few years back. FPC I've never tried. This is used for floating points. Don't know how good it is, but it's a pretty well-known compression algorithm, so should be good. Definitely try these things. One of the things that's really cool about ClickHouse is at any time on existing data, you can actually go ahead and alter the table and put in new codecs, and ClickHouse will apply them on any newly arriving data. So it's very easy to change the compression and codec scheme for your data on the fly. There was a quick question here that I'll treat. Are there partitioning schemes supported apart from time-based? Yes. Your partitioning is the way that you divide up a table and into parts so that ClickHouse knows how to break it up into pieces. You can use any value you want. Time-based partitioning is probably overall the most common way that people do it. And we do recommend that because it results in parts that are relatively large and that often align well with how you manage the data anyway. So for example, you might keep monitoring data for 7 days and then drop it. It's very easy to drop parts. So having it time-based would work very well. But you can use any formula here that you use. It just has to be something that can be computed from the table. As far as table size, there are no limits. If you have more than 1,000 columns in a table, we don't recommend that because it makes inserts very slow and can make it can make your database sluggish on startup because there are a lot of files it has to open. But if the table gets large, you can then break it up into pieces and shard it across multiple servers. There are the limits for a single table size are pretty high, so most people will never hit them. Okay, that was tip number 2. Let's talk about another one. This is a totally cool one that that I ran into recently and actually gave somebody some misinformation out on the ClickHouse Slack workspace. So let me dive in, explain what's going on here, and hopefully if that person is listening, you'll hear the right answer. So as we were just discussing, time is a pretty common component of table order. And the reason is that data tends to be, most big data tends to have a time dimension on it, as we call it, and that tends to be very significant in the management of the data. So for example, the most recent data is the most interesting, the oldest data is the least interesting. So organizing by time helps us address that. Um, we also have uh, uh, we will often order the data. In fact, we'll always order the data in large tables, and we'll often include the time in the ordering so that the data is correctly sorted. This also helps ensure things like compression, that compression will work more efficiently because values that, like monitoring values that increase over time will now be nicely arranged. We'll also choose something. This is actually a particularly important thing that will partition by some value that gets us about 1,000 parts on the server. And the reason for that is ClickHouse likes that number. It sort of balances the number of files it has to open when it's starting up, uh, and also gives it very long ranges of data that it can scan. ClickHouse parts can be very large, but the larger the parts are in general, the faster it is to scan them. So you'll tend to pick values that are uh, that result in pretty big parts. And in this case, partitioning by month is a very, very common pattern to use to get this kind of ideal number of parts per server. So, but what that this can actually lead to some bad results. So if you follow these rules, so we're partitioning by month, but let's say that we have data, and we're doing that for for overall efficiency of the ClickHouse server. But the problem is that we may actually be most interested in the data in the first day of that month. And so we'll have a bunch of queries that look like this, where we're saying, hey, I'm going to go select something where this is the day, this is this, I'll reduce some time value to start of day, and I'll call that the day. And then I'm going to compute some aggregates on this table where the day is equal to, and see how I do this, to start of day time. So I'm basically selecting out the data within that part that was associated with that particular day. Well, what's the problem? And we can see this if we look carefully in the logs, that when it actually selects this, because of the way that we have distributed this, the time is the further, because it's the highest cardinality value, it's on the right. But effectively, to go find all the records that that have the time that we're interested in, because they're broken up first by user ID and session ID, we have to read the entire part. And that's what these log messages are telling us, that we're reading. Marks are the are pointers into the blocks of compressed data. And what this is saying is, hey, we had to read all 28,544 of them just to answer this question. So we actually had to read the entire part to get an answer on just the data from one day. And here's the query speed and the amount we read. This is bad. We want to avoid reading all this extraneous data. So how do we do that? What we can do is we can actually add the time value in again, but have it higher up in the sort order. And so what we're going to do is go ahead and add to start of day time, and basically have time appear twice in the order, and it's in the primary key. We'll show that in just a second. But basically, we're putting it higher up so that ClickHouse can now find all the data for a single day, basically in one contiguous section of the part. So this is what we do. And it's useful right now to just review briefly what's going on under the covers in a merge tree table to explain why this, because it'll give you some context about why this works. So I mentioned that ClickHouse is a columnar storage, and this shows you what's going on inside a single part. There's, for each of the column, there's a pair of files. One is the little skinny one is an array that that basically indexes compressed blocks. These are called mark. It's called a mark array. And then you have the actual compressed blocks themselves. which are of greater or lesser lengths, depending on how big your data is. You also have what's called a sparse index. We call this a primary key index. It's not like a primary key index in MySQL, but it's basically allows us to find ranges uh, of data within that index very efficiently. So if we can use the sparse index, it will, if there's a column in there that we can use, it will actually allow us to index into particular parts of this and just read only those blocks and not have to read others. There's other things like skip indexes, but we won't talk about them here. So that's what's going on under the covers. And when we did this little change, we went got a question here, and I'll answer it in a second. Actually, I'll answer this right now. Common question that people ask is, oh, I hear you call this a primary key index. Does this actually enforce a constraint? In other words, if I put two values in a row that have the same primary key value, does ClickHouse spit them back to me? And the answer is no. And ClickHouse has no notion of referential integrity. This is in common with a number of data warehouses that have this behavior. So so what can happen is you can get duplicated data. I'm going to talk in another one of the tips about how to avoid that problem if deduplication is something you need to do. But it's a primary key index. We call it that, but it's really not a constraint. And it's in fact sparse because its real goal is to be very small and to locate a lot of data. To locate very small so it can fit in memory no matter how big the table is. It's not there to enforce referential integrity or constrain you to unique values. Getting back to our query, by making that simple change, now what we're looking at is we have a query which now runs quite a bit faster. It scanned less than a gig of data. It ran in effectively about a third of the time because there's some extra latency included in this because I'm going over the internet from my house to Oregon. But here's the key thing. We had, in this particular version of the table, we had 61,000 marks and it only read 5,000 of them, or less than 5,000 of them. So this is a huge improvement. And in fact, that's roughly a 30th of the data, not quite, but it's because I don't think there was quite a month in this part, but this shows you the effect of this optimization. So it's a cool one to consider. One thing that's really important is when you're playing around with this, test it. Don't assume. Normally when I set up a table, I wouldn't do this optimization. I would first run some tests, conclude, hey, my query looks like it's overreading, and then I would fix the index to address it. Getting on to the next issue, like, hey, if we don't have constraints, how do we deduplicate data? This is actually a great time to talk about ReplacingMergeTree, which is possibly the least known but most interesting of the merge tree table variants. So that picture I showed you is MergeTree is sort of the workhorse engine for ClickHouse. ReplacingMergeTree is a very interesting variant on it. And what it does is when you use ReplacingMergeTree, it automatically deduplicates the rows based on the order by. Here's an example. We have a table here called Sakila.film. If you've ever used MySQL, you'll know this is a sample table from the sample database. And we have this organized using the ReplacingMergeTree, and we have this this order by where we say it's ordered by language ID, studio ID, and the film ID, which actually turns out to be a MySQL primary key. And what this will do is if any row arrives that has the same values for these, ClickHouse will use that to replace the older one. So it doesn't just do so immediately. Sometimes you have to tell it to do this at query time, but the basic idea is any place where you have two rows with the same values, ClickHouse is going to knock out the older one. So this is a very powerful capability and can be used in a number of different ways. One is if you want to do, you have data where you like to do things like upserts, where either updated or inserted, RMT can do that. Another thing is if you have sort of you're trying to describe something stateful, where, for example, you have a mobile phone call and you're reading CDRs, call detail records, and you want to know, hey, what's the current state of this phone call? Um, RMT is great for that because you have a bunch of arriving records, and the last record is the one that wins, so you know the current state of the call. Another thing that it can do, and this is the example here, is it's very convenient for data that's replicated in from other databases like MySQL, and that's where this example comes from. So let's just push ahead and see how it works. So the best practice for this is to, excuse me, you have this version, and that this is an optional field, but it basically allows you to set a specific version to say, hey, and the highest number wins. If you don't do this, ClickHouse has a number that it can use internally that will serve the same purpose, but there are corner cases where it might not work. This allows you to be absolutely sure which record wins. So you'll put a record in. So for example, you'll insert, and then when you update, you're going to, here, let me just make sure I've got the, here we go. Okay, so we'll see the examples. When you update, you will actually put a record in, and you'll give the version, and then you'll say -1, and that's a convention that just says, hey, this is one I want to have disappear. And then you'll put a new one in, same version number, but +1. This is the one I want to have replace it. And then finally, if you want to make it disappear entirely, you put a last version number in with a -1, and then it deduplicates on these columns so that the last row is the one that you'll see. We'll show you how to actually make it disappear in just a second. Let's show some examples. So inserting a value in, we put in, here's a film that we're putting in, and the last two columns say, hey, this is version 0, and it's a 1 because I'm adding it. And then you do a select, and it just looks like an ordinary select out of merge tree. There you see the film. Let's say you want to update it, because Blade Runner had a bunch of different versions, so it's not the original version. We want to take that away, and we want to replace it by the director's cut. So here you go. So version number 3, a -1 to take it away, a 3 and a 1 to add it. And then when you do a select on this, it will you'll actually see 2 rows. And so then you're thinking, hey, I want my money back. This thing is supposed to deduplicate. Why didn't it happen? Well, the thing is that with RMT is based on the notion here is that the RMT algorithm will work even when the data is spread out over very long distances, like in multiple parts inserted at different times. And what ClickHouse does is it has kind of a lazy approach to merging the data. The data can merge in 2 ways. Let's show how they work. The first is when merges occur. So if you added the rows, row initially, and it's in one part, and then you had another part later on because you inserted the updates, when they merge in the background, what ClickHouse will do is it'll keep the newer rows. So they will, you'll now have the newer version of the data. So so that means if you wait long enough in small databases with not too many parts, or where the changes don't span parts, they will just merge after a while, but you can't count on it. And in fact, in ClickHouse, excuse me, you can never count on data actually being merged, because the parts, there's a number of reasons for this, but one big one is that parts reach a certain size, and then ClickHouse says, hey, that part is big enough, I'm going to leave it alone for a while, and it'll never touch it again. So if your change arrives after that's happened, it will never get merged. So how do we deal with that? Well, there's a thing called a final keyword, which you put after the table name, and what it will do is it will do an initial scan that will ensure that everything is properly merged. And in that case, you'll just get the 1 record. There's one other final trick, which is ClickHouse doesn't delete rows, it just leaves the last one in. And so, so you'll see you'll still see the row. And what we can do is there's a trick that works in all recent versions of ClickHouse that where we create a row policy. And that is a type of, it basically what it does is it adds a predicate that is going to be automatically inserted into any queries. And what this is doing is saying, hey, if you're looking at Sequila.film and sign it, if you're looking at Sequila.film and the sign is equal to -1, don't show it. And so that makes it disappear. There are some improvements in RMT that are replacing merge tree that are useful to know about. One is it's no longer necessary to put the final in. There is a setting that one of our guys at Altinity put in that just automatically appends it for you, so you don't have to change your code. The second thing is there's a very interesting new version of replacing merge tree done by Content Square, which will automatically delete the rows or garbage collect them, if you will, after a period of time. That was merged a couple months ago. It's still pretty experimental, but will eliminate the need for these row policies. Final thing on RMT, it is very powerful, but it also has some interesting performance consequences because of this need to merge things during the queries. There are a number of settings, so you should definitely check carefully. There's documentation. I did another talk on RMT at one of the recent meetups. You definitely want to play around with it a little bit to get the best performance. Okay, so we've still got a couple of good tricks to show you. Next one is RBAC command. So role-based access control and how to store them in Zookeeper. This turns out to be super useful. It's a recent feature put in by some of the folks at Ivan who are have a cloud for ClickHouse. So here's the problem. When you use role-based access control, they're great because you can create users and roles and profiles using SQL. The problem is that if you use this command that I just executed right here, it'll go into one ClickHouse server, and then it gets stored by default in this directory that's shown at the bottom. But if you have a cluster and you have other ClickHouse servers, they're not going to get it. So that user, when you go to those nodes, that user won't exist. There's a workaround for that, which is that you're going to need to use a special form of this create user commands. And first of all, you're going to need to include this on cluster command or clause, which says, hey, don't just execute it on this machine, but just execute it or on this server, execute it on every server in the cluster. Second thing, you're going to have to repeat that every time a new server is added. Third thing, because some of them have the user already and some of them don't, you're going to have to add this this if not exists syntax to say, hey, if you've already got it, just ignore what I'm telling you. So this is kind of painful. I mean, people have done it and lived to tell the tale, but there's an easier way now. And what you can do is when in your configuration for ClickHouse, you can enable replication of the RBAC data through Zookeeper. And this this path that you're seeing, the user's XML, just shows you well, that's where your XML stuff is. And then what you're doing right here is you're also putting what's called a Zookeeper path in, which will automatically replicate anything that's done during RBAC. So that's the critical part, is this replicated tag and the Zookeeper path. When you set this up, when you do these changes, they'll propagate automatically, which is really handy. And I use this. We use this in our own cloud. It's a super nice feature. So and stable. We have not seen any problems with it. Really good engineering on that. And one more thing. You can also see the actual RBAC settings. You can go in and select from system.zookeeper using this path, and it will show you. I just had one in this example, but if you had a bunch of them, they would become visible. One issue that this opens up, of course, is now you need to protect Zookeeper, because previously this stuff was hidden on the file system. People would actually have to break in to get it. If they can get into Zookeeper, they can see this information. If you had unencrypted passwords, for example, which is a no-no, they would see them. So something to think about. Let's do two more tips, and then we'll have some time for questions. So reducing data size and cost with TTL clauses. TTLs are great. It stands for time to live. And they started as a way, they were kind of like a feature a bit like Mongo. They started as a way to time out rows. And so what we see here is the TTL time plus interval. So what this is saying is, hey, delete my rows after 12 months. And what will happen is you put the data in, you just leave it for 12 months, and then ClickHouse in background will go ahead and remove it, and anything over 12 months and rewrite the part. It does this at intervals, so it's relatively efficient. So this is a great feature, and it's widely used. But what it inspired was a bunch of other ways to use TTL. So they include things like you can aggregate data as it becomes older. So for example, if you have a bunch of source records, you can collapse them into just one that sums over, for example, over a longer period of time to reduce data. You can do what are called moves, where you can move it across different types of storage. And finally, you can recompress data. This is kind of fun. So here what we have is a much more interesting TTL, which says, hey, recompress the data after a month and use ZSTD1, which is better for ints than LZ4. And after 6 months, really kind of jam it down even more using a higher level of ZSTD, more expensive, but reduces the data still more. And then finally delete it after 12 months. So what happens is you can actually see the effect of this very easily by going to the system.parts table and looking at the parts of a table that uses this. And here's an example. So I put in sort of chunks of 50,000 rows. The most recent stuff, which is using the default compression, has about 600,000 bytes. Go over a month, and it drops down to 327,000. So down by almost 50%. Go over 6 months, and this is going back to August, and you can see that it drops by another, a quarter to a third. So you can see the effect of these TTLs, and they're just squeezing down the data. There's no loss of information, but the data we've now saved, in this case, over 50%. By the time we get out to 6 months, we've saved over 50% of the storage, and of course, this can make queries quicker. As well, but the key thing is it saves storage. So that's a great feature. TTLs are definitely something to learn more about because it has many features and a number of useful capabilities. Okay, we're down to the final trick, which is my favorite by far, and that's using aggregation to simulate joins. This is a very powerful and kind of mind-bending capability. So, which is really where you start to, well, let me just give you the background, why this is something that we do. So when you have very large tables that contain different types, or very large databases with different types of entities, the standard way in relational databases that you would approach this is for each entity, you would have a separate table with its own primary key. That's traditional relational database design. So for example, third normal form. But when you have very big tables, you then sort of have a question, should I have separate tables like what I just described, or should I instead glom all of the entities into a single table? And the reason that you might want to do that is you can see them all at once. So you don't have to go to multiple tables. They might, if you have so you can just do a single scan of the table and see everything. So ClickHouse does have a bias for large tables where if you have something like this is, tracking transactions, we would stick these in a single table, even though they're in fact different entity types. The next thing is and in fact, what we're seeing here, this is a very important type of relationship. It's a master detail a relationship, kind of like invoice header and invoice rows. This is a transaction header and then transaction state changes. So a, a covering record that describes the transaction in general, and then detail records that tell what happened during that transaction and when it happened. So in typically, if we were, for example, if these were invoices and we were in a database like MySQL or Postgres, we would just do a join, and then we would be able to get a history of transaction state that would show detail records that included the header information, like, hey, when did the transaction start? The problem is that joins like this are actually an anti-pattern in big data systems, particularly if you want them to behave in real time. Why is that? Well, in order for this join to work, you may in fact end up doing things like moving data to different locations to make sure that the join keys line up correctly. So this join key, to have this join work, the transaction header row and the transaction state change rows, they have to be in the same place for the join to work. So you'll actually have operations. You see this in Spark, what's called a shuffle, where you may actually move heaps of data to different locations so that you can then join them efficiently. This does a couple of things. One is it's slow. The other thing is it's variable. So depending on the details of the join, you might have to move more or less data. What we're trying to do with real-time analytics on ClickHouse is to get very fast responses and to have that response be consistent, like to have 95% of the time the response is under a second. So what that means is we don't want to move data, and we don't want to have multiple scans on data. So instead, what we can do in ClickHouse is we can use aggregation. So aggregation has the property that it just does a single scan of the data to collect the information that we're aggregating. And it turns out that ClickHouse has some very powerful extensions that allow us to, to aggregate in a way that simulates a join. And so we have these two message types. We have the transaction header and we have the transaction change records. What we can do is group them. So we use group by, and that becomes our join key. And then ClickHouse has another totally cool feature, which it has the ability, it has an aggregate function called group array, which allows us to accumulate values in arrays in the order that they arrive. So that what happens is as this aggregation is proceeding, we're building up this array of data, which, and if we have multiple values that were like paired values, as in this case, they arrive in the same order. And then there's a final ClickHouse feature that's totally cool called array join, which basically explodes them back out to normal rows and and basically allows you to put the header IDs or header information into each row. So this is something that most databases cannot do. ClickHouse does it, and it does it quite well. So again, the group by key becomes your join key, and then you use these arrays to collect the data. Here's what the code looks like. It takes advantage of this group array function. It also takes advantage of a very powerful feature called an if combinator, which says, hey, if I'm looking at a message type of this particular, where it's X state, I want to stick it in the array. Otherwise, ignore the row. Again, without this if combinator, the group array wouldn't be helpful because we actually have different entities and we only want to collect these values for the entities for which they're relevant. And then there's this kind of cool if combinator on any that says, hey, grab any value you see. That's an aggregate function that's supported by some databases. ClickHouse does it very well or uses it commonly. And then we have an array join to explode them back out again. Here's what they look like. So this is the data. You can see the transaction ID was shared. They have the change information that came from the detail record and the start time, which came from the header. This is blindingly fast. And moreover, it will work no matter how broadly spread out your data is. You have one scan through the data and this works. So this actually means that instead of a join taking seconds or minutes, you can actually ask a question like this and often get it answered in a fraction of a second, even across multiple hosts. It's a very powerful feature. And why does it work? Well, it's basically because the ClickHouse does this vectorized scan, and what it's doing is as it's scan collecting this aggregated data, it's sticking it in hash tables. In a way, it's kind of like what a join does, and it just happens in this particular case. As long as you have not every join, this won't work for every join, but in this particular case, the aggregation is doing exactly the same under the covers, it's doing exactly the same accumulation of data that a join would, and that's why the whole thing works. It's a cool feature. If you understand this feature, you have some real insight into big data and distributed systems. And what I like about ClickHouse is it actually gives you the tools to take advantage of this type of query and uh, and then deliver very, very fast results over enormous data sets. So that's it for the tips and tricks today. Let me just summarize them really quickly. So here's the wallet size list, everything from reading S3 in parallel, using wildcards down to using aggregation instead of joins. In each case, if you understand how the trick works, you understand a lot more because you can do other tricks because you actually understand what it is that ClickHouse is doing under the covers. And the way I like to think about it is, or uh, the way I've learned about this is what you're really in some of these tricks, you're beginning to understand these are really tricks that depend on uh, sort of common practices in distributed systems. And the more you understand about these, the better you do. So got a question coming up. I'll take that at the end. Let me just, more information. This is just a limited number of things. Altinity YouTube channel. Uh, here are some videos that you might, the old tips and tricks from 2019. Replacing merge tree is pretty crazy. And has some ins and outs. So there's a talk on that. Actually, it's a double barrel talk that we did at a December meetup. Check that out. And then for some of the background about how ClickHouse works, queries, inserts, distributed query, check out a day in the life of ClickHouse query. We also have the Altinity blog, and then of course the ClickHouse documentation. And if you get really desperate, read the code. Sometimes some of these tricks, it's helpful that C++ is very well commented, and you can go in and figure out exactly what it's doing. Yeah, so uh, here's a great question. So the aggregation, and I'll take remaining questions for as long as they go. We're at time. So the question is, the aggregation looks awesome for real-time, near real-time analytics, but let's imagine you're pumping thousands of new records every second in a merge tree. In that case, would the aggregation work like some sort of materialized view, caching results, or would it be refreshed every time a new record is added? Okay, in the example I showed you, and let's go back to this because this was a comment that actually picks up on something that we're doing it dynamically. So you're going to repeat your work every single time. The so whatever the scan cost, if you ask this question 20 times, you'll run this scan 20 times, and you'll take the cost of computing these these group arrays and scanning the data. There is another way you can do this, which just builds on this. You can actually put this query into a materialized view so that if you know you're going to be asking this question constantly, you can go ahead and build a materialized view that runs this query on every arriving block of data and puts the results into a new table. And then you can select off that table. And what that means is you've got the data already pre-aggregated for you in effect. And so your query is going to be even faster. That is, if you had a case where you've got a bunch of data jamming in, you're constantly asking this question, you need to get a really fast response, like in the time it takes to render a page, build a materialized view, and based on this query, and then query that instead. And so that's exactly the question that this person asked is exactly that idea. And that's something that one of our support guys pointed out when he was reviewing this. Okay, so I think that's going to be it. If there are further questions, I'm happy to answer. I don't see, Kiara, I don't see any further questions in the chat or the Q&A.
No further questions.
Yeah, so thank you, everybody. I hope this was useful. Do come and visit us. Here we are. So we do Altinity.cloud. Of course, we basically let you run ClickHouse anywhere. You can do it in our cloud. You can run it in your own Kubernetes and be fully managed. Or you can do something completely weird. And for that, we have enterprise support. And we have hundreds of customers. Come visit us at altinity.com. We're happy to talk about this. And you can DM me either on the Altinity Slack workspace or the ClickHouse Slack workspace. Oh, questions here. Yes, let's cover them. Will this recording be downloadable? Yes, we'll send you a link, hopefully in 24 hours. Okay, here's a question. Let's say we're taking an ELT approach and ingesting data from a variety of sources directly into ClickHouse. Is there a way to enable some sort of row level permission or table level permission so that only platform engineers have access to the raw data, which may contain PII info, for example, before it gets encrypted? The short answer to that is yes. In fact, there's a very good answer. It's RBAC, role-based access control, which gives you the ability to enforce table level permissions. You can think of it as it's sort of a slightly enhanced version of the RBAC that's available on MySQL. So if you know that security model, the ClickHouse one is very similar to it. The other thing is it has row level, these things called row policies. And these are really these are incredibly helpful. One thing about row policies that is a problem with them that we're actually working on right now is there's sort of one policy per table per person. So if you have a lot of users in the system and a lot of tables, it's a little bit difficult to manage. We're actually putting in a feature to template them so if there's a smaller number that just work for everybody. Here's a question. Do you have any interesting examples of using an aggregating merge tree? Not off the top of my head, although, yeah, so this is a good tip. Do you know about simple aggregate functions? That's one of the things so aggregating merge trees are used to, to do aggregation, typically to pre-compute aggregates of various kinds. And there's a couple of optimizations that they're sort of complicated to use in some ways because they expose intermediate SQL results, intermediate aggregates, if you will. So you have to use special SQL syntax to read them. But there is something called a simple aggregate function, which is a data type that can be used like if you're just computing max, min, counts, things like that. These can be covered with simple aggregate functions so that when you're querying the aggregating merge tree, you don't have to use special merge syntax. So that's a key tip. I think beyond that, I'll have to think about this question, and I think in the next talk, I'll come back with some tricks around aggregating merge tree. It's a really powerful table type. So great. Thank you all for the questions and thank you for your attention. Please do contact me directly. As I say, you can DM me in the ClickHouse or the Altinity Slack workspaces. We're happy to answer questions or come to the site, fill out contact us if you want to talk more deeply about your apps. We're here to help. So thanks again. And thank you, Kiara, for your help on the webinar today. Okay. Have a good one, everybody.